All right, guys, so we are looking at the sine graph today, and we want to get a sense of what this graph looks like, and just a few new vocabulary words here to learn. It's the sine graph. There's really not a lot to it once you get to it, but it's a very useful function used to solve lots of problems these days. We call it a periodic function. So it can model things that repeat a lot. So anyways, y equals sine x. We're going to fill in this table and graph this together. And so sine of 0, and you may look back to the unit circle for this. I'm not going to spend a lot of time. We're going to fill this in pretty quickly here. But these are some of the basic values that we've found before, okay? So sine of 0 is what? So if we have our unit circle, here's 0 radians, and we're going to use that point 1, 0, right? So what would the sine of 0 be? It's the x value or the y value? The y value. So the sine of 0 is 0. So we're going to put a point at 0 for sure. So 0, 0. Okay. So our x-axis is our radian measure. Okay. Our y-axis is representing the sine of that radian measure. Pi over 6. That's when we have a 30, 60, 90 right triangle. Okay, so if we have 30 degrees in there, what would be the sine of 30 degrees? 0.5 or 1/2. And so at 0.6, or at pi over 6, we're going to be up here at 0.5. At pi over 4, that's when we have a 45-degree triangle, or 45, 45, 90. Our reference angle is 45. You guys remember what the sine of 45 is? Root 2 over 2. Now, as a decimal, we're going to have to approximate that. Get a calculator out. Root 2 over 2. You don't need a calculator. Let me just punch this in. You get 0.7, roughly 0.7. Okay. It's not exact, but it's about 0.7. So right above pi over 4, let's go up to about 0.7 here. Okay. Pi over 3 is when we had a 60-degree angle, reference angle. What was the sine of 60? You guys remember that? Root 3 over 2. Okay. And as a decimal value, let me work that out. We get 0.86. So let's round it to 0.9. Okay. And then pi over 2 is 90 degrees. So if we're pointed up at a height of 90 degrees, we're working with the point 0, 1. And so what's the sine going to be? Sine's your y-coordinate, which is 1. Okay. So I know I'm going through this process a little quickly here, but I just want you to see the shape that's emerging. So we get this little curve here, and then now we're in quadrant 2, and we're going to have the same triangles in quadrant 2. We're going to end up with the 60-degree angle in quadrant 2, and then the 45, and then the 30, and so it's just going to go back down, and so we're going to get the 0.9, the 0.7, the 0.5, back down to 0, because it's the same triangles, and just going back down to the x-axis. And so if I plot those, we have this kind of mound shape emerging. And then we're going to end up in quadrant 3. And quadrant 3 is going to give us negative sine values, but we're still going to have that negative, that 30-degree reference angle, that 45, and that 60. So we're still going to get the same values, but just in a negative, as a negative. Okay, so really we're going to get the negative 0.5, or negative 1/2. Sorry, this should be 1/2. The negative root 2 over 2, which is negative 0.7. The negative root 3 over 2, negative 0.9. And the negative 1, and so on. So we're just, if you copy those values down and make them negative, is what we end up with. Plot those values. Get something like this. And what's most important for us to see here is the shape that's emerging. Okay, this is what the sine curve looks like. And that's just one time around from 0 to 2 pi, right? That's one full circle. And you can, as we know, we can keep going around that circle. So if we go around the circle again, it's going to come back up, go back down, or we can go in the negative direction. It'll just continue this, and you get this wave-looking curve that continues on. Okay. When I have you graph this, I'm not going to have you graph it this way. The only reason this table's up here is just to get some points and have you see the pattern emerge. But when you're actually going to be graphing this, there's 5 points that you're going to focus on. You're going to focus on the starting point, which is on the x-axis on this one. Okay, so here's our first point, kind of in the middle. This maximum point, back down to the middle. The minimum point, back up to the middle. Okay, and so those are the 5 points we're looking at. And if you look at where they're happening in terms of our x values, okay, this is at 0. Next one's going to be at pi over 2. I'll just write it below it. Next one's at pi, which is, I'm going to put it as a fraction, 2 pi over 2. Next one's at 3 pi over 2. And the last one's 2 pi, which is 4 pi over 2. And so what you want to see here is when you're graphing, we're actually just going to mark off our x-axis by pi over 2. Okay. And so if I ask you to graph this sine function, let's just do it over here. I say graph y equals sine of x. What you would end up doing is saying, okay, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. Okay, so you mark off your x-axis by pi over 2. And at 0, you start in the middle. At pi over 2, you go to your highest point, which was what? What was the highest point? Do you remember? 1. Okay. At 2 pi over 2, you go back down to 0. At 3 pi over 2, you go to your lowest point, which was at -1. And then at 4 pi over 2, you go back up to the middle. And then you just kind of draw those curves in. And that's one, we call that one repetition or one period of the sine curve. Okay. It does keep going in both directions, but really that's about as much as you graph. Just here's one pattern of that sine curve. Okay, so now there's some questions below, and I want you to take a minute and find the answers to these questions. Okay. All right, so some basic quick questions here. What is the highest value y-coordinate for this function? 1. At what location or x-coordinate does this occur? Pi over 2. It reaches the height of 1 when we're at pi over 2. What is the lowest value? -1. Okay. Where does that happen? At what x-coordinate? 3 pi over 2. Okay. Since this function is periodic, meaning it repeats, does the exact same pattern forever from left to right, what is the domain of this function? How far left can it go? How far right can it go? As far as it wants, right? Okay. So, what about the range? What's the lowest it can go? -1. Should I use brackets or parentheses? And the highest? Okay, so it's contained in between -1 and 1. It won't go any higher than 1 or any lower than -1 on this one. Okay, and at what locations or x-coordinates is the value of the function equal to 0? So at 0, 2 pi over 2, or we could say pi, and at 2 pi. And then if it kept going either direction, like if we continued this going on, we could say 3 pi, 4 pi, and so on. Or we could say -pi, -2 pi, and so on the other direction. Because it repeats that pattern. Okay. Okay, the amplitude of a sine function is, in this case, is 1, since it goes up 1 and goes down 1 from the center, or we call it the equilibrium. And so the amplitude is going to be something that's important here. We're going to be able to change the amplitude and work with that, and as you'll see that in the next couple things. Okay. So number 3, we have the y equals 1/2 sine of x. Okay. So think about what the 1/2 would do to each of the y values. What do you think? What if you, by having the 1/2 in front, how would that change our y values? It would cut them all in half, right? So using a different color, from the previous problem, plot the points y equals 1/2 sine x on the same graph, and connect the dots with the smooth curve and answer the following questions. Okay, so back to the same graph. So wherever you had a point, just cut that point in half. So instead of 0.5, we're going to have it at 0.25. Okay, so find about the halfway mark between each of these points. Okay, so it's going to look like this. It's still going to have its 5 key points lined up with the other 5 key points. Okay, both graphs have the same x-intercepts. They both have their maximums at pi over 2. They both have their minimums at 3 pi over 2, but the difference is the y values are cut in half. Okay, so it's not reaching as high as the first graph. It's not reaching as low as the first graph. Okay. So go ahead and answer those questions. parts B through F on number 3. Okay, so what's the highest value? 0.5. I'm just going to put 1/2, but 0.5, yes. And where does that happen? Pi over 2. The lowest value? Negative 1/2 or negative 0.5. And this happens at 3 pi over 2. Since the function is periodic, does the same exact pattern forever from left to right. Is the domain going to be the same as the previous one? Yeah, from negative infinity to positive infinity. How about the range? Negative 1/2, comma, the 1/2, both in brackets. And at what x coordinates is this going to be equal to 0? 0, pi, and 2 pi for the ones we graphed, but we know it continues in each direction, okay? So again, here's, if you're given y equals 1/2 sine x, okay? If you guys are given y equals 1/2 sine x and asked to graph this number in front, as long as it's positive, is what we look at and say, okay, that's my amplitude. Okay, it's got to be positive though. Okay, if we had a negative 1/2 there, I'd just make the amplitude positive 1/2. So I know this is going to reach a max height from the equilibrium, from the center of 1/2 and go down 1/2. And so then I would say, okay, mark off. What do we count by? Pi over 2. 90 degrees. Okay? So 1 pi over 2, 2 pi over 2, 3 pi over 2, and then 2 pi, which is 4 pi over 2. Okay? We count by that, and we put our 5 points, go from equilibrium, from the middle to the max point, down to the middle, lowest point, back to the middle. Draw your curve. And then what would the maximum point be? What would the height be here? 1/2 this time, because that's your amplitude. And the minimum would be negative 1/2, because that's your amplitude. Okay. Okay, number 4, y equals negative sine x. You guys have some experience with functions. What do you think a negative sign does in front of a function? It reflects it across the x-axis, flips it upside down. Okay. So using a different color from the previous problems, plot the points appropriate to y equals negative sine x in the same graph, then connect the dots with a smooth curve. So if we go back and look at our two functions here, we got the first one in black, the second one in blue. Which one would I be flipping upside down? The first one. And so I'm going to use green now. And so I'm going to reflect my points. So instead of having a maximum at, and let's just use our 5 key points here, the ones we highlighted. Okay. So if I reflect that maximum from height 1, it's going to go down to negative 1 here. And so we're going to get this kind of upside down curve here. And then flex this way. Okay. I'll even highlight it for you because there's getting to be a lot of stuff on this graph here. Okay. So the negative sine curve is the sine curve flipped upside down. Okay. Still hitting those key 5 points. It just changes a max to a min and a min to a max. So what is the highest value of that function? 1. Where does it happen though? 3 pi over 2. What's the lowest value? Where does that one happen? Pi over 2. Since this function's periodic, what's the domain going to be? Okay, so it hits all your x values. And in the range, what's the lowest it will go? And the highest. Okay. At what locations does it 0, pi, and 2 pi? Okay. And what's the amplitude? 1. Good, because I just went over and said the amplitude always has to be positive. So you take the number out in front of the sign, in this case -1, and you make it positive, and so our amplitude's still going to, amplitude's always positive, and we get 1. Now we're going to think about translations, okay? If we put a +1 at the end of our function, what does that do? Moves the function up 1. So in this function, before we graph it, what do you think 3 is? How does that affect our graph? That's what we call the amplitude. Okay, it multiplies everything by 3. It stretches it out. Okay, and we'll see that in a second here. It's a positive number, so we can leave it 3. And then that +1 is going to move it up 1. Okay, so if I go through my graph, what I do here is I make sure my x-axis is marked off by pi over 2. And it is, because here's pi. This one's pi over 2. This is 2 pi over 2. This is 3 pi over 2. And this one's 4 pi over 2. Okay, those are the 5 points we need here. And you start in the middle, but you got to be careful here. This whole thing's been moved up 1 unit. So now our middle is at height 1, and you don't have to draw it in, but I'm going to do this just to say, okay, our middle's been moved up. That's our equilibrium. So at 0, we start at the middle. Okay. At pi over 2, we reach our maximum height. Now, what's our amplitude? 3. And so I need to go up 3 from the middle. So if I'm already at 1 and I need to go up 3 more, what's my maximum going to hit? I'm going to be at 4. So right above the pi over 2, I hit my maximum. At 2 pi over 2, I come back down to the middle of my graph, or the equilibrium, which is at height 1. At 3 pi over 2, I go 3 below the equilibrium, which would be 1, 2, 3 at -2. And then at 4 pi over 2, I go right back up to the middle. And so here, draw your smooth curve through this. That's one period of our function. So let's see if we can go through answering these questions. B says, what is the highest value for the function? We see it's at 4. At what location does this occur? What's the lowest value? -2. And this happens at 3 pi over 2. Using a different color, extend that pattern all the way from -pi to 3 pi. So we went from 0 to 2 pi, and we want to just keep this graph going, and they say use a different color, so I'll use red in mine. So if I want to extend it, so if I'm extending it from the right side, I'm going to go back up to my max and back down to the equilibrium. So we kind of get half of the graph right here. Yeah, if you don't have a different color, you can use a dash. And then on the left-hand side, I'm going to drop down to the min and back up to the equilibrium. Okay. Or you could use a highlighter or whatever. So the part I'm going to highlight is the original. Okay. But just keep in mind, the reason I'm having you draw the rest is just this keeps going and repeating, and just looks, we call it a wave function. Okay. Those of you that know some stuff about science, what travels in waves? Sound. What else? Light. Water. Good. Okay. The ocean. There's lots of things that travel in rays. Okay. There's gamma rays. So they travel in waves, right? And so guess how they're modeled mathematically? Using the sine curve. Okay. All right. Number 6. Okay, take a look at this function. So there's a few things that we need to pay attention to. So first of all, there's a negative sign. What does that negative sign tell us? Negative. What about at the graph? We're going to be reflecting it, okay? Okay? Reflect. With an L, okay. Reflect. Okay, and then what does the 2 tell us? That's our amplitude. Okay? Now, you just said sound travels in waves. Okay? Think about amplitude with sound. Okay? If you change that volume control on you, well, if you increase the volume, what you're doing is you're working with the sine curve, and you're increasing that amplitude. So the larger that amplitude, the louder the sound. The smaller the amplitude, the softer the sound. Okay. Now think about translations. What is this minus pi over 2 going to do? It's in parentheses. The translation here. It moves it which way? Moves to the right pi over 2. Okay. And there's nothing outside the parentheses, so we're not moving it up or down. So our equilibrium is still going to be at 0, but our starting point's no longer going to be at 0, 0. We're moving right pi over 2. Okay. So we need to put all these things together. So our x-axis is still marked off by pi over 2. So here's 1 pi over 2. This is 2 pi over 2. 3 pi over 2. 4 pi over 2. But because we're moving right pi over 2, I'm going to have to go one more. 5 pi over 2. Okay. So now, where's the first point I'm going to put on the graph? Good. On the equilibrium, pi over 2. What was our amplitude? 2. Amplitude's always positive, but it was negative, so I'm not going to go to the max first. I'm going to go to the min first. So right below, so my first point I got, my second point is going to be below the 2 pi over 2 at the minimum, because it's a negative curve, negative sine curve, and then back up to the equilibrium, and then to your maximum, back down to the equilibrium. All right, so those are the 5 key points that we use when we're graphing the sine. And this time it's shifted to the right pi over 2. And it's reflected, so it's upside down. It went to its minimum first, then to its maximum. What's the highest value? 2. Where does it happen? Nope. Okay, 4 pi over 2. So you could put 4 pi over 2, but what does that reduce to? 2 pi. What's the lowest value? -2. Mr. Marsh. Okay, lowest function we said was -2. Where does that happen? At 2 pi over 2, which is the same thing as pi. Okay. Then using a different color, extend the pattern in both directions. Okay, so at 3 pi, where do I put my height at 3 pi? -2. At 0, where do I put it? At 2. At -pi over 2, where am I going to put my height? 0. And at -pi, -2. Okay. So homework is going to be like this. You're working on worksheet 7. Doing number 2 and 7 through 10. Okay.